Hi guys, we've already been working with the first part of the fundamental theorem of calculus. It's right over here in the right corner. And so we know the derivative of the accumulation function, where small f is the function that we're accumulating the net area for, is f of x. So it is small f. Okay, so we worked with that a bit last time. It's time to introduce the second part of the fundamental theorem of calculus. And to do that, I'm going to use some little bit different notation. And it's in the second part, we have a definite integral on this side. Now over here we have some new using big F. We have big F of b minus big F of a. Okay, that you can think of the definite integral as being that. Okay. So let's see what this means. Okay. First of all, remember, as we accumulated area, so the two functions, and we've seen them before. The black function is my acceleration function. The blue function is the velocity function that we generated from the acceleration function. And we showed, I didn't show how I did it, right? But I showed that as we're accumulating area here, right? So if I'm halfway, the halfway point I should be at 30. And notice that my accumulation function, my value is 30. I'm sitting right here at 30 when x is 1/2, okay? So there's a one-to-one correspondence between the value of our velocity function and the accumulated net area under the acceleration curve. Well, for just right now, I'm going to come and call this acceleration curve, instead of calling it the black curve, instead of calling it A like we have been, I'm going to call it F. Okay. How can I get this line that I got here? Well, what we know is that f is the derivative as we accumulate, right, of the thing that of the function that we're accumulating, right? So if I can just reverse the differentiation process, that's called getting the antiderivative. Okay, so if we already have f and I want to get the antiderivative, I'm going to reverse the differentiation process. Okay, and when I take the antiderivative, I'm going to have big F. So there's where that notation big F comes from. I'm somehow reversing the differentiation process. I'm going to first do it, and we're actually going to do it in most simple cases here, because we're going to do it a lot in calculus 2. But let's look at what function do we have, or given for the acceleration function initially. We're given the function, it's just the constant function 60, right? So this is just a function. If I'm using small f, this is just, for this first segment, we have the function f equals 60 in that first hour. Okay, he's accelerating at a constant rate of 60. Okay, well, how would I reverse that? If I know this is the derivative, it's just 60, okay, the function f equals 60 is derivative, how could I go get the antiderivative? Well, let's just think of what we do. What gives us 60 as the derivative? 60x, right? You guys agree? If we have f is 60, okay, then it has to be, to have gotten to that 60, we're going to learn a rule here in a little bit, but big F of x would have to be 60x. Now, so the derivative of 60x is 60. Ah, that looks like that works. But what about the derivative of 60x plus 3? What is that? Well, the 3 falls out when I do the differentiation, so f prime has got to be f, right? f prime of x, if f of x is 60x plus 3, well, that falls out, so it's also 60. Well, what if it, instead of 3, it was 75? Well, it doesn't matter. This constant falls out, right? So that's also 60. So what we have to say is that when the antiderivative, we always have to put a plus c. Okay? Because this could be any number over here. If f of x is 60, its antiderivative is then got to be 60x plus c, because the derivative of 60x plus c will give me, so I've just shown f prime of x is f of x, and that's what I need. Okay? So we got 60x plus c as my antiderivative. So this is the new big idea, the antiderivative. I want to make another video. We're going to kind of use this idea.